When we say something is big, we usually mean big relative to something else. A house is big compared to a person. A mountain is big compared to a house. A planet is big compared to a mountain. And so the chain of comparisons continues upward, through stars, through stellar neighborhoods, through entire galaxies, and eventually to structures so vast that even the language of comparison begins to lose its usefulness. The Andromeda Galaxy occupies a peculiar position in this chain. It is the nearest large galaxy to our own Milky Way, which means it is close enough to study in extraordinary detail, yet it is also far enough away and large enough that the very question of its size turns out to be surprisingly difficult to answer. The difficulty is not merely technical, although there are plenty of technical challenges. The difficulty is partly conceptual. What do we mean by the size of a galaxy? Do we mean the region where most of the stars are concentrated? Do we mean the full extent of its gravitational influence? Do we mean the volume filled by its dark matter halo, a component we cannot see directly, but whose presence we infer from the motions of everything we can see? Each of these definitions gives a different answer, and each of those answers has changed over time as instruments have improved, as theoretical models have been refined, and as the very concept of what a galaxy is has evolved. To understand how big Andromeda really is, it helps to understand how we arrived at our current picture, what we thought it was at various points in the history of astronomy, what measurements were used, how those measurements were corrected and revised, and what we still do not know. The story of Andromeda's perceived size is inseparable from the story of how humanity came to understand the scale of the universe itself. For most of recorded history, the idea that anything could exist outside the Milky Way was simply not part of the intellectual framework available to astronomers. The Milky Way was the universe, and the faint smudges of light that could be seen in the sky with the naked eye, including the one in the constellation Andromeda, were assumed to be nebulae, clouds of gas or unresolved clusters of stars within our own system. The Persian astronomer Abd al-Rahman al-Sufi described the Andromeda Nebula in his Book of Fixed Stars around the year 964, calling it a small cloud. That description is notable because it is one of the earliest known references to the object in any written record, but it tells us nothing about the object's true nature or size. Al-Sufi had no way of knowing what it was. He saw a faint, diffuse patch of light, and he recorded it. The observation was accurate in the sense that the object is indeed visible to the unaided eye under good conditions, appearing as a faint elongated smudge roughly the apparent size of several full moons laid side by side, though much dimmer and less sharply defined. Centuries later, when telescopes became available, the nature of these nebulae became a subject of active debate. Charles Messier catalogued the Andromeda Nebula in 1764 as M31, the 31st entry in his list of objects that might be confused with comets. Messier was a comet hunter, and his catalogue was essentially a list of things that were not comets, objects that appeared fuzzy and diffuse in telescopes but remained fixed in position relative to the stars. The catalogue was a practical tool, not a theoretical statement, but it had the effect of grouping together objects that were in fact wildly different from one another. Some of Messier's entries are indeed gas clouds within the Milky Way, others are globular clusters, and some, including M31, are entire galaxies far beyond the boundaries of our own. But in Messier's time, there was no way to distinguish these categories. The instruments were not powerful enough, and the conceptual framework did not yet include the possibility of other galaxies. The question of whether nebulae like M31 might be separate systems of stars, comparable in size and composition to the Milky Way, had been raised as a philosophical speculation as early as the 18th century. Immanuel Kant, drawing partly on the ideas of Thomas Wright, suggested in 1755 that some of the nebulae might be what he called island universes, vast collections of stars at enormous distances. This was an extraordinary leap of reasoning, but it remained a hypothesis without empirical support. The telescopes of the time could not resolve individual stars within M31, and without the ability to measure distances, there was no way to determine whether the object was a relatively small cloud of gas within the Milky Way, or an immense stellar system far beyond it. The two possibilities implied radically different sizes. If M31 was a nearby gas cloud, it might be a few light-years across. If it was a distant galaxy, it might be tens of thousands of light-years across or more. The angular size on the sky was the same either way, but the physical size depended entirely on the distance, and the distance was unknown. Progress came slowly. William Herschel, working in the late 18th and early 19th century, attempted to catalogue and classify nebulae systematically, and he initially believed that many of them could be resolved into individual stars with sufficiently powerful telescopes. He later revised this view, concluding that some nebulae were genuinely diffuse, composed of a luminous fluid rather than stars. His son, John Herschel, continued this work, but the fundamental question of the nature and distance of the nebulae remained unresolved. The debate persisted throughout the 19th century and into the early 20th century, becoming one of the central controversies in astronomy. On one side were those who argued that the Milky Way was essentially the entire universe, and that all nebulae were objects within it. On the other side were those who maintained that at least some nebulae were external systems, island universes in their own right. This debate came to be known, somewhat retrospectively, as the Great Debate, and it reached a kind of formal culmination in 1920 when Harlow Shapley and Heber Curtis presented opposing views at the National Academy of Sciences in Washington. Shapley argued for a large Milky Way and maintained that the spiral nebulae, including M31, were relatively nearby objects within our galaxy. His estimate of the Milky Way's size was based on his studies of globular clusters, which he used as distance markers. His model of the Milky Way was in fact too large, partly because he did not account for the dimming effect of interstellar dust, which made distant objects appear farther away than they actually were. Curtis, on the other hand, argued for a smaller Milky Way and maintained that the spiral nebulae were external galaxies. He pointed to the appearance of dark lanes in some spirals, which he interpreted as analogous to the dust lanes observed in the Milky Way, and he noted that novae observed in the Andromeda Nebula were much fainter than novae in the Milky Way, suggesting that M31 was at a much greater distance. Curtis was closer to the modern view, but neither side had the definitive evidence needed to settle the question. The debate was inconclusive at the time, and it was not until a few years later that the question was resolved by direct observation. The resolution came from Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the largest telescope in the world. In 1923 and 1924, Hubble identified individual Cepheid variable stars in the Andromeda Nebula. Cepheid variables are stars whose brightness varies in a regular periodic way, and the period of their variation is directly related to their intrinsic luminosity. This period luminosity relationship had been established by Henrietta Swan Leavitt in 1912, based on her study of Cepheids in the Small Magellanic Cloud. Leavitt's discovery was one of the most consequential in the history of astronomy, because it provided a method for determining distances. If you know how bright a star actually is, and you measure how bright it appears, you can calculate how far away it must be. Hubble applied this method to the Cepheids he found in M31, and determined that the nebula was approximately 900,000 light-years away. This was far beyond the boundaries of the Milky Way as it was then understood, and it meant that M31 was not a gas cloud or a star cluster within our galaxy, but an entirely separate galaxy, an island universe of its own. Hubble's distance estimate was a milestone, but it was not correct by modern standards. His value of roughly 900,000 light-years was too small by about a factor of 2.5. The error arose from several sources, the most important of which was a confusion between two different types of Cepheid variable stars. The classical Cepheids that Leavitt had studied in the Magellanic Clouds follow one period luminosity relationship, but there is another class of pulsating stars, now called Type II Cepheids, or W Virginis stars, which are intrinsically fainter and follow a different relationship. In the 1940s, Walter Bardy, also working at Mount Wilson, was able to resolve individual stars in the central regions of M31 for the first time, taking advantage of wartime blackout conditions in Los Angeles, which reduced light pollution. Bade found that the stars in the central bulge of M31 were of a different type than those in the spiral arms, and he introduced the concept of stellar populations, dividing stars into population 1, which are younger and found in the disk and arms, and population 2, which are older and found in the bulge and halo. This work led to a recalibration of the Cepheid distance scale. In 1952, Baird announced that the distance to Andromeda was roughly double what Hubble had estimated, approximately 2 million light-years. Subsequent revisions, incorporating improvements in the calibration of Cepheid luminosities, corrections for interstellar extinction, and the use of additional distance indicators, have brought the current best estimate to approximately 2.5 million light-years, or about 770 kiloparsecs. This distance is important not only in its own right, but because it determines the physical size we infer from the angular size we observe. Andromeda's visible disk, as seen in deep photographic and CCD images, extends across roughly 3 degrees on the sky, though this depends on the depth of the exposure and the wavelength of observation. 3 degrees is about 6 times the apparent diameter of the full moon, which often surprises people who are accustomed to thinking of galaxies as tiny specks, visible only through telescopes. In fact, Andromeda is one of the largest objects on the sky in terms of angular extent, but most of its light is spread over such a large area that it is too faint to see easily, especially from light-polluted locations. Only the bright central core is visible to the naked eye. The full extent of the galaxy, including its faint outer regions, has been revealed only through long-exposure imaging. At a distance of 2.5 million light-years, an angular diameter of roughly 3 degrees corresponds to a physical diameter of approximately 130,000 to 140,000 light-years for the bright stellar disk. This is already a substantial number. It means that if you could somehow travel at the speed of a light, it would take you about 130,000 to 140,000 years to cross the galaxy from one side to the other. For comparison, the Milky Way's bright stellar disk has been estimated at roughly 100,000 light-years in diameter, though more recent studies have suggested it may be somewhat larger, perhaps 170,000 to 200,000 light-years, when faint outer structures are included. The comparison between Andromeda and the Milky Way has been a subject of ongoing revision. For many decades, Andromeda was considered significantly larger and more massive than the Milky Way. It was often described as the dominant member of the local group, the small cluster of galaxies to which both the Milky Way and Andromeda belong. More recent measurements have complicated this picture, suggesting that the Milky Way may be more comparable in mass to Andromeda than was previously thought, or possibly even slightly more massive depending on the method used and the uncertainties involved. But we will return to this comparison later. The diameter of the bright stellar disk is only one way to describe the size of Andromeda, and in many respects it is not the most physically meaningful one. Galaxies do not have sharp edges. The density of stars decreases gradually as you move outward from the center, and the point at which you say the galaxy ends depends on how faint a surface brightness you are willing to detect. Modern surveys using sensitive instruments have detected stars belonging to Andromeda at much greater distances from its center than the classical disk diameter would suggest. In 2005, a team using the Isaac Newton telescope on La Palma published results from the Pan-Andromeda Archaeological Survey, or PANDAS, and related programs, showing that Andromeda's stellar halo, the diffuse cloud of stars surrounding the main disk, extends to at least 500,000 light-years from the center and possibly farther. This halo is not a smooth, uniform distribution of stars. It is structured, containing streams, shells, and clumps that are the remnants of smaller galaxies that have been torn apart by Andromeda's gravitational field over billions of years. These structures are the fossil record of Andromeda's growth through the accretion of smaller systems, a process that is predicted by the standard model of galaxy formation in a universe dominated by cold, dark matter. The stellar halo, vast as it is itself embedded in an even larger structure, the dark matter halo. Dark matter cannot be observed directly because it does not emit, absorb, or reflect light, but its presence is inferred from its gravitational effects on visible matter. The rotation curve of Andromeda, that is the plot of how fast stars and gas orbit the center of the galaxy, as a function of their distance from the center, remains flat, or even rises slightly at large radii, rather than declining as would be expected if the mass of the galaxy were concentrated in the visible disk. This flat rotation curve implies the existence of a large amount of unseen mass extending well beyond the visible boundaries of the galaxy. Estimates of the size of Andromeda's dark matter halo vary depending on the model used and the definition of the halo boundary, but a common convention is to define the halo in terms of the virial radius, the radius within which the average density of matter is a certain multiple of the critical density or the mean density of the universe. Under this convention, Andromeda's dark matter halo has a virial radius on the order of 800,000 to perhaps over 1 million light-years. This is an astonishing number. It means that the gravitational sphere of influence of the Andromeda Galaxy extends across a volume of space millions of light-years in diameter, far larger than the visible galaxy that we see in photographs. In 2015, a study using observations from the Hubble Space Telescope's cosmic origin spectrograph provided evidence that Andromeda's gaseous halo, the circumgalactic medium, extends to at least 1.3 million light-years from the centre, and possibly as far as 2 million light-years in some directions. This measurement was made by observing the absorption signatures of ionized gas in the spectra of distant quasars whose light passes through Andromeda's halo on its way to us. The gas is extremely tenuous, far too diffuse to be detected by its own emission, but it leaves a detectable imprint on the light of background sources. If these measurements are correct, and if we define the size of the galaxy to include this gaseous halo, then Andromeda's effective diameter could be on the order of 2 to 4 million light-years. At that scale, the halos of Andromeda and the Milky Way are likely already overlapping, which means that in some sense the two galaxies are already in contact, even though their main stellar disks are still 2.5 million light-years apart. The idea that the halos of these two galaxies may already overlap leads naturally to the question of what will happen in the future, and this too is relevant to understanding Andromeda's size, because the size of a galaxy is not a static quantity. Galaxies grow over time by accreting gas, merging with other galaxies, and drawing in matter from the intergalactic medium. Andromeda shows abundant evidence of past mergers and accretion events. Its stellar streams and shell structures, as mentioned earlier, are the debris of smaller galaxies that have been consumed. Studies of the stellar populations in these streams have revealed a diversity of chemical compositions and ages, suggesting that Andromeda has absorbed numerous smaller systems over its history. One particularly notable structure is the giant stellar stream, a long, coherent arc of stars extending from the southeast side of the galaxy, which is believed to be the remnant of a dwarf galaxy that was tidally disrupted as it fell into Andromeda's gravitational potential well. The properties of this stream, including its metallicity and the kinematics of its stars, have been used to reconstruct the orbit and mass of the progenitor galaxy, providing a window into the history of Andromeda's growth. The future evolution of Andromeda is also a matter of active study. Observations of the radial velocity of M31, primarily through Doppler measurements of its spectral lines, have long established that Andromeda is approaching the Milky Way at approximately 110 km per second. For much of the 20th century, it was uncertain whether this approach was purely radial or whether there was a significant tangential component to the motion, which would determine whether the two galaxies would actually collide or merely pass close to each other. Measuring the tangential motion of an object 2.5 million light-years away is extremely challenging, because the angular displacement on the sky is tiny, even over a span of years. However, in 2012, a team using the Hubble Space Telescope reported the first direct measurement of Andromeda's proper motion, its motion across the sky. The results indicated that the tangential velocity is much smaller than the radial velocity, which means that the two galaxies are on a nearly head-on collision course. Current models predict that the Milky Way and Andromeda will begin to interact gravitationally in about 4 to 5 billion years, with the main merger occurring perhaps a billion years after that. The result will be a single, larger galaxy, sometimes informally called Milkomeda, whose size will be larger than either progenitor. But returning to the present, the question of Andromeda's mass is intimately connected to the question of its size, because the spatial extent of any gravitationally bound system is fundamentally related to the total amount of mass it contains and the way that mass is distributed. The total mass of the Andromeda Galaxy has been estimated using several different methods, including rotation curve analysis, the kinematics of satellite galaxies, and globular clusters orbiting M31, gravitational lensing studies, and dynamical modelling. The results have varied considerably, reflecting the difficulty of the measurement and the sensitivity of the answers to the assumptions built into the models. Earlier estimates tended to place Andromeda's mass at roughly 1 to 2 trillion solar masses, making it significantly more massive than the Milky Way. However, more recent studies, particularly those incorporating data from the Gaia Space Observatory and updated dynamical models, have suggested that the Milky Way may have a mass comparable to, or even exceeding that of Andromeda. A study published in 2018, for example, estimated Andromeda's mass at approximately 800 billion solar masses, while other analyses have yielded values closer to 1.2 or 1.5 trillion solar masses. The discrepancies arise from differences in the data used, the radial range over which the mass is measured, and the treatment of the dark matter halo's outer boundary. The question of which galaxy is more massive remains an area of active research, and it is possible that the two are sufficiently close in mass that the answer depends on the specific definition and method used. The number of stars in Andromeda is another measure of its size, and here too the estimates have evolved over time. Andromeda is often said to contain approximately 1 trillion stars, roughly twice the number estimated for the Milky Way. This figure is based on measurements of Andromeda's total luminosity and assumptions about the average luminosity of its stars, a quantity known as the stellar mass-to-light ratio. The total luminosity of Andromeda in the visible part of the spectrum is roughly 25 billion times the luminosity of the Sun, but most of this light comes from a relatively small number of bright, massive stars. The vast majority of stars in any galaxy are low-mass red dwarfs, which are individually very faint but collectively numerous. The estimate of 1 trillion stars assumes a certain distribution of stellar masses, known as the initial mass function, which describes how many stars of each mass are formed in a given episode of star formation. If the initial mass function in Andromeda differs from the one assumed, which is possible given that conditions may vary between galaxies and even between regions within a single galaxy, then the total number of stars could be significantly different from the standard estimate. The structure of Andromeda is worth describing in some detail, because the way its mass and stars are distributed in space is what gives the galaxy its characteristic appearance and determines its physical extent. Like the Milky Way, Andromeda is a spiral galaxy, but it is classified as a type Sa, Sb, indicating that it has a prominent central bulge, well-defined spiral arms, and no bar structure, or at most a weak one. This last point has been the subject of some debate. Observations in the infrared, which penetrate dust more effectively than visible light, have suggested the presence of a bar-like structure in the inner regions of Andromeda, though it is less pronounced than the bar in the Milky Way. The spiral arms of Andromeda are not as sharply defined as those in some other spiral galaxies, and they show signs of disturbance, possibly due to past interactions with satellite galaxies. The galaxy is inclined at an angle of roughly 77 degrees to our line of sight, which means we see it nearly edge-on, giving it the characteristic elongated shape familiar from photographs. The central bulge of Andromeda is large and luminous, contributing a significant fraction of the galaxy's total light. Within the bulge lies a compact nucleus, and within that nucleus, observations have revealed a double structure, 2 brightness peaks separated by about 1.5 parsecs. This was discovered by Todd Lauer and colleagues using the Hubble Space Telescope in 1993. One of the brightness peaks is thought to coincide with the location of a supermassive black hole, while the other is interpreted as a concentration of stars in an eccentric disk orbiting the black hole. The mass of the supermassive black hole at the center of Andromeda has been estimated at roughly 100 to 230 million solar masses based on the velocities of stars and gas in the nuclear region. This is significantly more massive than the black hole at the center of the Milky Way, Sagittarius A star, which has a mass of about 4 million solar masses. The presence of a more massive central black hole in Andromeda is consistent with the general trend observed in galaxies, where more massive and more luminous galaxies tend to harbour more massive central black holes, a relationship known as the M-sigma relation, linking the black hole mass to the velocity dispersion of stars in the bulge. The disk of Andromeda, where most of the star formation activity occurs, is rich in gas and dust, particularly in the spiral arms. The distribution of neutral hydrogen gas in Andromeda has been mapped using radio telescopes operating at the 21 centimeter wavelength, the characteristic emission line of atomic hydrogen. These maps reveal a complex extended gas disk that stretches to radii beyond the optical disk, with a warped structure in its outer regions. The warp of the gas disk is a common feature in spiral galaxies and is often attributed to gravitational interactions with companion galaxies or the accretion of gas from the intergalactic medium at oblique angles. In Andromeda, the warp may be related to past interactions with M32 or M110, 2 of its most prominent satellite galaxies. The gas disk, including the warped outer regions, extends the measurable size of Andromeda beyond what is seen in starlight alone, reinforcing the point that the size of a galaxy depends on what component you are measuring. The satellite system of Andromeda is itself an indicator of the galaxy's size and gravitational reach. As of the most recent surveys, Andromeda is known to have at least several dozen satellite galaxies, small dwarf galaxies gravitationally bound to M31 and orbiting within its dark matter halo. The most prominent satellites are M32, a compact elliptical galaxy very close to Andromeda's disk, and M110, or NGC205, a dwarf elliptical galaxy visible in many photographs of M31. Beyond these, surveys such as Pandas have discovered numerous faint dwarf spheroidal galaxies in the outer halo of Andromeda, some of which are extremely low in surface brightness and were detected only through careful analysis of resolved stellar populations. The distribution of these satellites in space is not random. A significant fraction of Andromeda's satellites appear to lie in a thin, roughly planar structure, sometimes called the Great Plane of Andromeda, which is oriented nearly edge-on as seen from the Milky Way. This planar distribution has been the subject of considerable debate because it is not easily explained by the standard cosmological model, in which dark matter halos are expected to have a roughly spherical distribution of subhalos. The existence of such a plane, if confirmed as a dynamically coherent structure rather than a chance alignment, could have implications for our understanding of galaxy formation and the behavior of dark matter on galactic scales. The furthest known satellite galaxies of Andromeda are found at distances of several 100,000 light-years from M31's centre, which gives another measure of the galaxy's gravitational sphere of influence. Some of these remote satellites may be in the process of falling into Andromeda for the first time, while others may have been orbiting for billions of years, their orbits gradually evolving due to dynamical friction and tidal effects. The total population of satellites is uncertain, because the faintest dwarfs are extremely difficult to detect, and ongoing and future surveys are expected to discover more. A particularly informative way to think about the size of Andromeda is to consider the galaxy at different wavelengths of light. In visible light, the galaxy appears as a bright bulge surrounded by a disk with spiral arms, and the overall extent is roughly what was described earlier, about 130,000 to 140,000 light-years for the bright disk, with faint outer extensions reaching considerably further. In the ultraviolet, which traces young, hot stars and regions of recent star formation, Andromeda's appearance changes somewhat. The bulge, which is dominated by older, cooler stars, becomes less prominent, while the spiral arms and star-forming regions in the disk become more conspicuous. The ultraviolet observations made by the Galaxy Evolution Explorer, or GALEX satellite, revealed a ring of enhanced star formation in the disk of Andromeda at a radius of roughly 30,000 to 35,000 light-years from the centre. This ring is thought to be the result of a close passage by the satellite galaxy M32, which may have plunged through Andromeda's disk roughly 200 million years ago, creating a density wave that propagated outward and triggered a burst of star formation. The ring structure illustrates how interactions with companion galaxies can shape the morphology and the effective star-forming size of a galaxy. In the infrared, which traces warm dust heated by starlight and also reveals older stellar populations whose light peaks at longer wavelengths, Andromeda shows a complex network of dusty filaments and rings associated with the spiral arms. Observations from the Spitzer Space Telescope and the Herschel Space Observatory have provided detailed maps of the dust distribution, which closely follows the gas distribution and marks the regions where new stars are forming. The dust emission extends throughout the disk and into the inner regions of the spiral arms, but it is largely absent from the outer halo, where the gas and dust have been stripped or were never present in significant quantities. The total mass of dust in Andromeda has been estimated at roughly 50 to 60 million solar masses, based on the far infrared and submillimeter emission. This dust is a small fraction of the total mass of the galaxy, but it plays a crucial role in star formation, providing the raw material from which new stars condense, and in the chemistry of the interstellar medium, where molecules form on the surfaces of dust grains. In X-rays, Andromeda reveals yet another aspect of its size and structure. X-ray observations, primarily from the Chandra X-ray Observatory and XMM Newton, have detected hundreds of point-like X-ray sources within Andromeda, many of which are X-ray binary systems, pairs of stars in which material from one star is being transferred to a compact companion either a neutron star or a black hole. The X-ray emission from these binaries traces the distribution of certain types of evolved stellar systems and provides information about the history of star formation and binary evolution in the galaxy. In addition to point sources, diffuse X-ray emission has been detected from hot gas in the bulge and inner disk of Andromeda, as well as from the circumgalactic medium at larger radii. The properties of this hot gas, including its temperature, density, and chemical composition, are important for understanding the processes by which gas is heated and cycled through the galaxy, including supernova explosions, stellar winds, and feedback from the central black hole. At radio wavelengths, the 21-centimeter hydrogen line maps already mentioned reveal the full extent of the neutral gas disk, which extends to about 75,000 to 80,000 light-years in radius, or roughly 150,000 to 160,000 light-years in diameter. This is somewhat larger than the bright optical disk. Radio continuum observations at other frequencies reveal synchrotron emission from relativistic electrons spiraling in the galaxy's magnetic field, tracing the distribution of cosmic rays and magnetic fields throughout the disk. The magnetic field structure of Andromeda appears to be organized on large scales, with a coherent field following the spiral arm pattern, which is consistent with dynamo models of magnetic field generation in disk galaxies. The strength of the magnetic field in Andromeda is estimated to be a few microgauss, comparable to the Milky Way. Each of these different views at different wavelengths reveals a different component or aspect of the galaxy, and each implies a slightly different effective size. The optical disk is one size, the gas disk is larger, the stellar halo is larger still, the dark matter halo is vastly larger, and the gaseous circumgalactic medium may be the most extended of all. This multiplicity of sizes is not a shortcoming of our measurements, but a reflection of the physical reality that a galaxy is not a single, well-defined object, but a complex, multi-component system whose different parts have different spatial extents and different physical properties. The history of how Andromeda's size has been measured and revised is also a history of the instruments and techniques that have been developed to study distant objects. The early visual observations using the naked eye and small telescopes could only reveal the bright central regions. Photographic plates, introduced in the late 19th century, allowed longer exposures and the detection of fainter outer regions, gradually expanding the apparent size of the galaxy. The introduction of CCD detectors in the late 20th century brought another leap in sensitivity, allowing even fainter structures to be detected and measured. Space-based telescopes, free from the blurring effects of Earth's atmosphere, provided sharper images and access to wavelengths blocked by the atmosphere, including the ultraviolet and much of the infrared. Radio telescopes, operating at wavelengths entirely different from visible light, revealed the gas component that is invisible to optical telescopes. Each new instrument and technique has, in effect, made the galaxy larger, by revealing components and structures that were previously below the threshold of detection. This progression is not unique to Andromeda. It is a general pattern in the history of observational astronomy. As instruments improve, objects that were once thought to have well-defined boundaries are found to extend farther and farther into space. The Milky Way itself has undergone a similar expansion in its perceived size. Early estimates placed its diameter at a few tens of thousands of light-years, but modern surveys have revealed stellar streams, tidal tails and halo stars extending to distances of several 100,000 light-years from the galactic center. The same is true of other galaxies studied in sufficient detail. The notion of a galaxy as a compact, well-bounded system with a definite edge is a simplification. In reality, galaxies fade gradually into the intergalactic medium, and the distinction between a galaxy and its environment is a matter of degree rather than a sharp boundary. The mass distribution within Andromeda has been studied in detail through a variety of dynamical techniques. The rotation curve, obtained by measuring the Doppler shifts of spectral lines from gas and stars at different positions along the galaxy's disk, is one of the most fundamental tools. As noted earlier, the rotation curve of Andromeda remains approximately flat at large radii, with rotation velocities of about 225 to 250 km per second, depending on the radius and the tracer used. This flatness is a strong indication of a massive dark matter halo, because the visible mass alone cannot account for the observed velocities. The total mass enclosed within a given radius can be estimated from the rotation curve using straightforward Newtonian dynamics, under the assumption that the mass distribution is approximately spherically symmetric at large radii. Within the optical disk, the enclosed mass is on the order of several hundred billion solar masses, but the total mass within the virial radius is much larger, reflecting the contribution of the dark matter halo. The dynamics of Andromeda's satellite galaxies and globular clusters provide complementary information about the mass distribution at larger radii beyond the edge of the detectable gas disk. By measuring the velocities of these objects and comparing them with models, it is possible to constrain the total mass and the radial profile of the dark matter halo. Andromeda has a very rich globular cluster system, with over 450 confirmed globular clusters, significantly more than the approximately 150 known in the Milky Way. These clusters span a wide range of distances from the center, from the inner bulge to the outer halo, and their kinematics provide valuable data for mass modeling. The globular cluster system also contains information about Andromeda's assembly history, because some of the clusters may have been brought in by accreted dwarf galaxies rather than having formed in situ. Distinguishing between these two populations based on their positions, kinematics, ages, and chemical compositions is an active area of research that connects the study of Andromeda's size and mass to the broader question of how large galaxies are assembled over cosmic time. The chemical composition of Andromeda's stars, gas, and dust is another dimension of the galaxy that is relevant to understanding its size and evolution. Spectroscopic surveys of individual stars in Andromeda's disk, bulge, and halo have revealed gradients in metallicity, the abundance of elements heavier than hydrogen and helium, as a function of position within the galaxy. In general, the stars in the central regions are more metal-rich, reflecting a longer and more intense history of star formation and chemical enrichment, while the stars in the outer disk and halo tend to be more metal-poor. However, the metallicity distribution in the halo is not uniform. Some of the stellar streams and substructures in the halo have metallicities that are higher than expected for a smooth, well-mixed halo, suggesting that they originated from relatively massive dwarf galaxies that had undergone significant chemical evolution before being accreted by Andromeda. The presence of these chemically distinct substructures in the outer halo extends the effective size of the galaxy in a chemical sense, because it means that Andromeda's gravitational influence has drawn in material from a volume of space much larger than the bright disk, incorporating the products of star formation and chemical evolution from many smaller systems. The star formation history of Andromeda has been reconstructed through a combination of techniques, including the analysis of color magnitude diagrams of resolved stellar populations, the fitting of spectral energy distributions of unresolved regions, and the comparison of observed properties with stellar evolution models. These studies have shown that Andromeda experienced a major episode of star formation in the past, perhaps 8 to 10 billion years ago, followed by a decline in the overall star formation rate. The current rate of star formation in Andromeda is relatively modest, estimated at roughly 0.2 to 0.4 solar masses per year, which is lower than the Milky Way's rate of roughly 1 to 2 solar masses per year. This difference is somewhat surprising given that Andromeda is generally considered to be at least as massive as, and possibly more massive than, the Milky Way. The lower current star formation rate may reflect differences in the gas supply, the efficiency of gas consumption, or the effects of past interactions and mergers that may have heated or expelled gas from the star-forming regions of the disk. The star formation history has implications for the size of the galaxy as well, because the spatial extent of the star-forming disk has likely changed over time, expanding or contracting in response to the availability of gas and the dynamical effects of interactions. The morphology of Andromeda's spiral arms is another feature that carries information about the galaxy's history and present state. The arms are not perfectly regular. They show asymmetries, bifurcations, and disturbances that are thought to be the result of gravitational interactions with companion galaxies. Simulations have shown that the passage of M32 through or near Andromeda's disk could have generated many of the observed features, including the ring of star formation mentioned earlier, the warped outer disk, and various asymmetries in the spiral arm pattern. These simulations require specifying the mass, orbit, and initial conditions of M32, which introduces considerable uncertainty, but the general conclusion is that Andromeda's present-day morphology is significantly shaped by its interactions with its satellites. This means that the visual impression of a large, symmetric spiral galaxy, while broadly correct, is an oversimplification. The actual structure is more complex and more dynamic, with features that reflect billions of years of gravitational interactions, mergers and accretion events. The question of Andromeda's size also connects to the broader context of galaxy sizes in general. Galaxies span an enormous range of sizes, from tiny dwarf galaxies containing only a few million stars and spanning a few hundred light-years to giant elliptical galaxies containing trillions of stars and spanning several 100,000 light-years or more. The Andromeda Galaxy falls near the upper end of this range among spiral galaxies. It is one of the largest and most luminous spiral galaxies known in the local universe, though it is surpassed in size by some very large spirals such as UGC 2885, sometimes called Rubin's Galaxy, which has a disk diameter of roughly 800,000 light-years. The size distribution of galaxies is related to the distribution of dark matter halo masses, which in turn is predicted by cosmological simulations based on the cold dark matter model with dark energy, known as the lambda CDM model. In this framework, the mass function of dark matter halos follows a characteristic shape, with many more low-mass halos than high-mass ones, and the efficiency with which baryonic matter, the ordinary matter that makes up stars, gas and dust, is converted into visible galaxies depends on the halo mass in a complex non-linear way. Low-mass halos are relatively inefficient at forming galaxies because supernova-driven winds and other feedback processes can expel gas before it can form stars. Very high-mass halos are also relatively inefficient because heating from the central black hole and other processes can suppress gas cooling and star formation. The sweet spot, where galaxies are most efficient at converting baryons into stars, is at intermediate halo masses, roughly corresponding to galaxies like the Milky Way and Andromeda. This framework provides a theoretical context for understanding why galaxies like Andromeda have the sizes and masses they do. They inhabit dark matter halos of a particular mass range, and the interplay between gravity, gas dynamics, star formation, and feedback determines the final size and structure of the visible galaxy within that halo. The gravitational lensing signal of Andromeda provides yet another perspective on its mass and size. Gravitational lensing occurs when the gravitational field of a massive object bends the path of light from a more distant source, distorting the apparent shape or position of the background object. In the case of Andromeda, the galaxy is not massive enough or distant enough to produce strong lensing effects such as multiple images or Einstein rings, but it can produce weak lensing and microlensing signals. Microlensing, in which the gravitational field of a compact object such as a star or a stellar mass black hole temporarily brightens a background star, has been used to search for dark compact objects in Andromeda's halo. The AGAPE, POINT-AGAPE, and WECAPP surveys, among others, have monitored millions of stars in Andromeda over extended periods, looking for the characteristic brightening events that would indicate microlensing. The results have provided constraints on the fraction of Andromeda's dark matter that could be in the form of compact objects such as primordial black holes or massive compact halo objects, generally finding that such objects cannot account for a large fraction of the total dark matter mass. These surveys also incidentally provide information about the stellar content and variability properties of Andromeda's stellar population. Returning to the straightforward question of physical dimensions, it is useful to summarize the different size scales associated with Andromeda. The bright optical disk, as typically photographed in visible light, has a diameter of approximately 130,000 to 140,000 light-years, or about 40 to 43 kiloparsecs. This includes the central bulge, which has an effective radius of several thousand light-years, and the disk with its spiral arms. The neutral hydrogen gas disk extends somewhat farther, to a diameter of roughly 150,000 to 160,000 light-years, or about 46 to 49 kiloparsecs. The stellar halo, composed of old stars and the debris of accreted satellite galaxies, has been detected to radii of at least 500,000 light-years, or about 150 kiloparsecs from the center. The dark matter halo, as inferred from dynamical studies, has a virial radius on the order of 800,000 to 1 million light-years, or about 250 to 300 kiloparsecs, and the gaseous circumgalactic medium, detected through absorption line studies, may extend to 1.3 million light-years or more, corresponding to 400 kiloparsecs or more. Each of these numbers represents a different physical component and a different measurement technique, and all of them are subject to uncertainty and ongoing refinement. These numbers gain additional meaning when placed in the context of the local group. The local group is a small collection of galaxies dominated by two large spirals, the Milky Way and Andromeda, along with approximately 80 or more smaller galaxies, most of which are satellites of one or the other of the two giants. The overall size of the local group is roughly 10 million light-years across, and its total mass is on the order of a few trillion solar masses, with most of that mass residing in the dark matter halos of the Milky Way and Andromeda. The separation between the two large galaxies, 2.5 million light-years, is comparable to the estimated virial radii of their dark matter halos, which reinforces the point that the halos may be overlapping or nearly so. The Triangulum Galaxy, M33, the third largest galaxy in the local group, is located about 2.7 million light-years from the Milky Way and about 750,000 light-years from Andromeda. M33 is a smaller spiral galaxy with a disk diameter of roughly 60,000 light-years and a mass of perhaps 50 billion solar masses, much smaller than either of the two dominant spirals. The spatial relationship between Andromeda and M33 is of particular interest, because some models suggest that M33 may be a satellite of Andromeda that is in the process of falling toward it, while other models suggest that the two are on their first approach to each other. Observations of a bridge of neutral hydrogen gas between M33 and Andromeda have been reported but remain somewhat controversial, and the dynamical relationship between the two galaxies is still not fully resolved. The process by which Andromeda reached its current size is a central question in the study of galaxy formation and evolution. In the lambda-CDM framework, galaxies grow through a combination of two processes: the accretion of gas from the intergalactic medium and the cosmic web, and the merging of smaller galaxies. The relative importance of these two channels varies with time and with the mass of the galaxy. At early times, when the universe was denser and more gas-rich, smooth gas accretion was likely the dominant mode of growth, with cold gas flowing along filaments of the cosmic web into the centers of dark matter halos, where it could cool, condense, and form stars. At later times, as the universe expanded and the gas supply diminished, mergers with other galaxies became relatively more important. For a galaxy like Andromeda, both processes have likely played significant roles. The numerous stellar streams and substructures in the halo attest to a rich history of minor mergers, the accretion of dwarf galaxies with masses ranging from millions to perhaps a few billion solar masses. The question of whether Andromeda has also experienced a major merger, a collision with another galaxy of comparable mass, is more difficult to answer. Some features of Andromeda's structure, including the prominence and kinematics of the central bulge, the disturbed morphology of the inner disk, and certain aspects of the stellar population, have led some researchers to propose that Andromeda underwent a major merger roughly 2 to 3 billion years ago. This hypothesis is supported by some simulations but is not universally accepted, and it remains a topic of active investigation. The interstellar medium of Andromeda, the gas and dust between the stars, is an important component of the galaxy that contributes to its overall size and mass. The total mass of the interstellar medium in Andromeda, including both atomic and molecular gas, is estimated at roughly 5 to 10 billion solar masses. The molecular gas, which is the immediate precursor to star formation, is concentrated in the spiral arms and the ring-like structure mentioned earlier. Its distribution has been mapped using observations of carbon monoxide, CO, which serves as a tracer for the much more abundant but harder to detect molecular hydrogen. The atomic gas, traced by the 21 cm hydrogen line, is more widely distributed, extending to larger radii. The interstellar medium is not static. It is constantly being recycled as stars form from gas, evolve and return material to the medium through stellar winds and supernova explosions. This cycle of star formation and gas recycling determines the chemical evolution of the galaxy, and influences the rate at which new stars are formed, which in turn affects the galaxy's luminosity and, indirectly, its perceived size in different wave bands. The dust in Andromeda's interstellar medium plays a role in shaping the galaxy's appearance at optical wavelengths. By absorbing and scattering starlight, the dust lanes visible in photographs of Andromeda are regions of relatively high dust concentration, typically associated with the spiral arms. The effect of dust is to redden and dim the light of stars behind it, making them appear fainter and redder than they actually are. This effect, known as interstellar extinction, must be corrected for when measuring the properties of individual stars or the integrated light of the galaxy. The distribution and properties of dust in Andromeda have been studied extensively using infrared and submillimeter observations, which detect the thermal emission from dust grains heated by starlight. The dust temperature in Andromeda varies with position, being warmer in regions close to hot young stars and cooler in more quiescent regions. The total mass of dust is related to the total mass of metals, elements heavier than helium, in the interstellar medium, and thus to the overall chemical enrichment history of the galaxy. The globular cluster system of Andromeda deserves further discussion because it provides important constraints on the galaxy's size, mass, and formation history. As mentioned earlier, Andromeda possesses over 450 confirmed globular clusters, the largest known population among galaxies in the local group, and one of the largest of any galaxy studied. The globular clusters span a wide range of ages, metallicities, and spatial positions. The most metal-poor clusters, with metallicities less than about 1/10 of the solar value, tend to be found in the outer halo and are generally old, with ages of 10 to 13 billion years. These clusters are thought to be relics of the earliest phases of galaxy formation, either having formed in situ from primordial gas or having been brought in by accreted dwarf galaxies. The more metal-rich clusters tend to be found closer to the center of the galaxy, in the bulge and inner disk, and they are associated with later generations of star formation. Some of the globular clusters in Andromeda are exceptionally luminous and massive, rivaling or exceeding the most massive globular clusters in the Milky Way. The brightest of these, G1, also known as Male 2, has a mass of approximately 10 million solar masses and has been the subject of speculation that it might harbour a central intermediate mass black hole, though this remains uncertain. The overall properties of the globular cluster system, including the total number, the mass function, the spatial distribution and the kinematics, are used as inputs for dynamical models of the galaxy and provide independent constraints on the total mass and the shape of the dark matter halo. One aspect of Andromeda's size that has received increasing attention in recent years is the so-called stellar mass of the galaxy, the total mass contained in stars as opposed to gas, dust, or dark matter. The stellar mass is typically estimated from the total luminosity and the mass-to-light ratio, which depends on the age, metallicity, and initial mass function of the stellar population. For Andromeda, the stellar mass is estimated at roughly 100 to 150 billion solar masses, making it one of the most stellar massive spiral galaxies known. This stellar mass is spread across the bulge, disk, and halo, with the bulge and disk containing the majority. The effective radius of the stellar mass distribution, the radius within which half of the total stellar mass is contained, is on the order of a few kiloparsecs for the bulge and 5 to 7 kiloparsecs for the disk, depending on the assumed model. The half-mass radius is a useful measure of the galaxy's stellar extent, because it captures the overall concentration of the mass without being sensitive to the precise definition of the outer boundary. The surface brightness profile of Andromeda, the variation of surface brightness with distance from the center, has been measured with high precision using both ground-based and space-based observations. The bulge follows a Cercic profile with a Cercic index of approximately 2 to 2.5, intermediate between the exponential profiles typical of disk-dominated galaxies and the steeper profiles of classical elliptical galaxies. The disk follows an approximately exponential decline in surface brightness with radius, with a scale length of about 5 to 6 kiloparsecs. At large radii beyond the main disk, the surface brightness drops to extremely low levels, but it does not reach zero. The extended stellar halo contributes a faint diffuse glow that has been detected to the radii mentioned earlier, several 100,000 light-years from the center. Measuring this faint outer emission is technically challenging, because it requires extremely deep observations with careful control of systematic effects such as sky subtraction, scattered light, and contamination from foreground stars. The velocity field of Andromeda, mapping how fast different parts of the galaxy are moving toward or away from us, provides a three-dimensional picture of the galaxy's dynamics. The rotation of the disk produces a characteristic pattern in which one side of the galaxy is blue-shifted, moving toward us, and the other side is red-shifted, moving away. The amplitude and shape of this rotation pattern yield the rotation curve, which, as discussed, is used to infer the mass distribution. but the velocity field contains more information than just the rotation. Deviations from pure circular rotation can indicate the presence of non-axis symmetric structures such as bars, spiral arms, or tidal distortions. In Andromeda, such deviations have been detected and are being used to refine models of the galaxy's structure and to probe the effects of interactions with satellite galaxies. The metallicity gradient in Andromeda's disk, the change in the average chemical composition of stars and gas as a function of distance from the centre, is another feature that encodes information about the galaxy's history of star formation and gas flows. In general, the inner regions of the disk are more metal-rich than the outer regions, reflecting the fact that star formation has been more intense and more prolonged in the centre. The slope of the metallicity gradient and its evolution over time are sensitive to the balance between infall of metal-poor gas from the intergalactic medium, outflow of metal-enriched gas driven by supernova explosions and stellar winds, and radial mixing of gas and stars within the disk. Measuring the metallicity gradient in Andromeda requires spectroscopy of individual stars or HII regions at multiple positions across the disk, which is observationally demanding at a distance of 2.5 million light-years, but has been accomplished for bright targets such as red giant branch stars and luminous blue supergiants. The age gradient in Andromeda's stellar population is related to but distinct from the metallicity gradient. Studies of the resolved stellar populations in different parts of the galaxy have shown that the mean age of the stellar population generally increases with distance from the plane of the disk and from the centre of the galaxy. The younger stars are found in the disk, particularly in the spiral arms and the star-forming ring, where they have formed within the last few 100 million years. The oldest stars are found in the outer halo, where the stellar population is predominantly composed of ancient metal-poor red giant branch stars with ages comparable to the age of the universe. This age stratification is a natural consequence of the inside-out growth of the galaxy, in which the central regions formed first and the outer regions were assembled later through the accretion of satellite galaxies and the gradual settling of gas. A question that is often asked in the context of Andromeda's size is how it compares not just to the Milky Way but to the wider population of galaxies. Among spiral galaxies, Andromeda is large but not uniquely so. Galaxies such as the Pinwheel Galaxy, M101, have optical disk diameters comparable to or slightly larger than Andromeda, though their total masses are typically lower. As mentioned, some very large spirals like UGC 2885 have disk diameters several times that of Andromeda. Among all galaxies, the largest are typically giant elliptical or CD galaxies, found at the centres of massive galaxy clusters. The central galaxy of the Abell 2029 cluster, IC 1101, has been estimated to have a stellar envelope extending to radii of over 2 million light-years, making it among the largest known galaxies by any measure. These enormous galaxies have grown through the repeated merging of many smaller galaxies over cosmic time, a process known as hierarchical assembly. Andromeda, while much smaller than these extreme cases, is still a very large galaxy by any standard, and its prominence in our sky is as much a consequence of its proximity as of its intrinsic size. The comparison between Andromeda and the Milky Way has been a recurring theme in this discussion, and it is worth examining in more detail because it illustrates some of the challenges and uncertainties involved in measuring galaxy sizes and masses. One fundamental difficulty is that we are inside the Milky Way, which makes it harder to measure its properties from the outside. We cannot take a photograph of the Milky Way from above, the way we can for Andromeda. Instead, we must infer its structure from our vantage point within the disk, using techniques such as star counts, parallax measurements, proper motion surveys, and the mapping of gas and dust. This perspective effect introduces biases and uncertainties that do not apply to the study of Andromeda. Conversely, Andromeda is seen from the outside, which makes its overall structure easier to discern, but its distance means that faint features and individual low-mass stars are harder to study. The two galaxies are thus complementary in the information they provide, and the comparison between them is one of the most productive avenues of research in galactic astronomy. Recent work using data from the Gaia Space Observatory has significantly revised our understanding of the Milky Way's mass and size. Gaia has measured the positions and motions of over 1 billion stars in the Milky Way with unprecedented precision, allowing much improved models of the Milky Way's structure and dynamics. One of the key results has been a revised estimate of the Milky Way's total mass, including the dark matter halo. which is now thought to be in the range of 1 to 1.5 trillion solar masses. This is comparable to, or even slightly higher than some recent estimates of Andromeda's mass, suggesting that the two galaxies may be more evenly matched than was previously believed. The disk of the Milky Way, based on recent studies, may also be larger than the traditional estimate of 100,000 light-years in diameter, with some analyses suggesting a diameter of 170,000 to 200,000 light-years when faint outer structures are included. If these larger estimates are correct, the difference in disk size between the Milky Way and Andromeda is smaller than was once thought. The rate at which Andromeda and the Milky Way are approaching each other, approximately 110 kilometers per second, sets a timescale for their eventual merger. At this rate, and accounting for the gravitational acceleration that will increase the approach speed as the galaxies get closer, the first close passage is expected in roughly 4 to 5 billion years. Simulations of the merger process using N-body and hydrodynamical codes have shown that the initial encounter will be a dramatic gravitational event, pulling long tidal tails of stars and gas from both galaxies and distorting their shapes. After the first passage, the two galaxies will swing apart, then fall back together, eventually merging into a single larger galaxy over a period of about 1 to 2 billion years after the initial interaction. The final product is expected to be an elliptical or possibly a lenticular galaxy, larger than either progenitor, with a more diffuse and less structured distribution of stars. This future merger will not significantly affect the solar system or the Earth, because the distances between individual stars are so large that direct stellar collisions are extremely unlikely, but the night sky will be dramatically different, with the orderly structures of the Milky Way and Andromeda replaced by a more amorphous cloud of stars. The collision of Andromeda and the Milky Way is sometimes presented as a catastrophic event, but from the perspective of the galaxies themselves, it is a perfectly ordinary process that has happened countless times in the history of the universe. Galaxy mergers are a fundamental mechanism of galaxy growth, and the properties of many of the largest galaxies observed today, including their masses, sizes, shapes, and stellar populations, are the cumulative result of many such mergers over billions of years. The fact that Andromeda and the Milky Way are currently two separate galaxies, rather than a single merged system, is a consequence of their particular formation histories and their present-day separation, which is large enough that they have not yet interacted strongly, though as noted their extended halos may already be overlapping. The distance to Andromeda, 2.5 million light-years, is itself a remarkable number when considered in the context of what it means for observation. Light from Andromeda that we observe today left the galaxy 2.5 million years ago, during the early Pleistocene epoch on Earth, before the appearance of modern Homo sapiens. Every observation of Andromeda is therefore a snapshot of the galaxy as it was 2.5 million years in the past. The current state of Andromeda, including the positions of its stars, the extent of its gas, and the location of its spiral arms, is slightly different from what we observe, because the galaxy has continued to evolve during the light travel time. For most purposes, 2.5 million years is a very short time compared to the timescales of galactic evolution, which are measured in billions of years, so the difference between the observed state and the current state is negligible. But it is a useful reminder that all astronomical observations involve a look backward in time, and that the further away an object is, the deeper into the past we're seeing. This light travel time consideration also applies to the question of what Andromeda looked like in the distant past, and what it will look like in the distant future. By observing other galaxies at greater distances, which are seen at earlier cosmic times, astronomers can study the ancestors of galaxies like Andromeda, and trace the evolution of galaxy sizes and structures over the age of the universe. Surveys of distant galaxies have shown that the average size of galaxies has increased over time, both because individual galaxies grow through accretion and merging, and because the population of galaxies shifts toward larger sizes as the universe ages. At redshifts of 1 to 2, corresponding to look-back times of roughly 8 to 10 billion years, galaxies comparable in mass to Andromeda were typically smaller in size, with effective radii roughly half to two-thirds of their present-day values. This size growth is observed across all types of galaxies, though the detailed mechanisms differ between spirals and ellipticals and between different mass ranges. The chemical evolution of the universe is also reflected in Andromeda's properties. The first generation of stars in the universe formed from the primordial hydrogen, and helium produced in the Big Bang contained no elements heavier than lithium. These early stars produced heavier elements through nuclear fusion in their cores and released those elements into the interstellar medium through supernova explosions and stellar winds, enriching the raw material available for subsequent generations of stars. Over billions of years, this process of chemical enrichment has built up the abundances of elements such as carbon, nitrogen, oxygen, iron, and many others, which are now observed in the gas and stars of galaxies like Andromeda. The chemical composition of Andromeda's stars spans a wide range, from the most metal-poor halo stars with metallicities a few hundredths of the solar value, to the most metal-rich disk stars with metallicities comparable to or exceeding the solar value. This range reflects the cumulative history of star formation and chemical enrichment in the galaxy and its many progenitor systems. The fact that Andromeda is visible to the naked eye makes it one of the most distant objects that can be seen without a telescope, along with a handful of other galaxies such as the Triangulum Galaxy, M33, and perhaps a few others under ideal conditions. The apparent brightness of Andromeda, integrated over its full extent, corresponds to a visual magnitude of approximately 3.4, which is comparable to a moderately bright star. However, because this light is spread over an area of several square degrees on the sky, the surface brightness is quite low, and only the bright central core is easily visible without optical aid. The contrast between Andromeda's total brightness and its low surface brightness is a consequence of its large angular size, and it illustrates the general principle that extended objects can be harder to observe than point-like objects of the same total brightness. The visual appearance of Andromeda in photographs has become one of the most recognizable images in astronomy, and it has shaped public perceptions of what galaxies look like. The classic image shows a bright, elongated core surrounded by a fainter, diffuse disk with dark dust lanes crossing the near side. The spiral arms are visible in deeper images, and individual star-forming regions, globular clusters, and satellite galaxies can be identified. Modern wide-field imaging surveys have extended this picture to much larger radii, revealing the faint outer disk and the stellar halo with its streams and substructures. The Hubble Space Telescope's mosaic image of Andromeda, composed from thousands of individual exposures and covering a large fraction of the galaxy's disk, is one of the highest resolution images ever taken of another galaxy, resolving over 100 million individual stars. This image provides a vivid sense of the sheer number of stars in a large galaxy and the complexity of its structure on all scales. The study of Andromeda has contributed to many areas of astronomy beyond the direct question of its size. It has been central to the development of the extragalactic distance scale, the calibration of standard candles such as Cepheid variables and tip-of-the-red giant branch stars, the understanding of stellar populations and stellar evolution, the detection and characterization of dark matter, the dynamics of galaxy mergers and interactions, and the testing of cosmological models. In many of these areas, Andromeda serves as a benchmark, the closest large galaxy, and therefore the one that can be studied in the greatest detail. Its proximity means that individual stars can be resolved and studied spectroscopically, something that is not possible for most galaxies, which are too distant for their stellar populations to be broken down into individual objects. This has made Andromeda an indispensable laboratory for studying the physics of galaxy formation and evolution. The ongoing and planned surveys of Andromeda continue to refine our understanding of its size and structure. The PANDAS survey, mentioned earlier, has provided the most comprehensive map of the stellar halo to date, but deeper and wider surveys are planned or underway using next-generation facilities. The Vera C. Rubin Observatory, expected to begin full operations in the mid-2020s, will conduct the Legacy Survey of Space and Time, which will repeatedly image the entire southern sky to unprecedented depth. Although Andromeda is in the northern sky and not directly in the survey footprint, similar facilities in the north are being developed and will extend the census of faint outer structures around Andromeda and other nearby galaxies. The James Webb Space Telescope, launched in December 2021, has the sensitivity and resolution to study individual stars in Andromeda in the infrared, probing stellar populations and star formation in regions that are obscured by dust at optical wavelengths. These and other facilities will continue to expand our picture of Andromeda, pushing the measurable boundaries of the galaxy ever outward and refining the estimates of its mass, size, and structure. It is also worth noting that the definition of Andromeda as a discrete object, separate from its surroundings, is itself a simplification that breaks down at the larger scales. In the lambda CDM cosmological model, galaxies are embedded in a cosmic web of dark matter filaments and voids, and the boundary between a galaxy's halo and the intergalactic medium is not a sharp surface but a gradual transition. The matter in the outskirts of Andromeda's halo is not cleanly separated from the matter in the intergalactic medium of the local group. Gas flows in and out of the halo, satellite galaxies orbit within it, and are sometimes tidally disrupted, and the halo itself is slowly evolving as it accretes additional matter from the surrounding environment. The size of the galaxy, in this view, is a dynamic and somewhat arbitrary quantity, defined by the observer's choice of measurement and threshold, rather than by a physical boundary. This idea that the size of a galaxy is a matter of definition and measurement rather than an absolute physical fact is central to understanding the answer to the question posed at the beginning. How big is the Andromeda Galaxy really? The answer is that it depends on what you mean by Andromeda and what you mean by size. If you mean the region where you can see stars in a typical photograph, the answer is about 130,000 to 140,000 light-years across. If you mean the region where you can detect stars with the deepest available observations, the answer is at least 1,000,000 light-years across. If you mean the region filled by gas associated with the galaxy, the answer may be 2 to 4 million light-years across. If you mean the region dominated by the galaxy's dark matter halo, the answer is roughly 1.5 to 2 million light-years across. And if you consider the full extent of the galaxy's gravitational influence, including its effects on satellite galaxies, and on the kinematics of the local group, the answer is even larger and shades into the territory of the local group as a whole. Each of these answers is correct in its own terms, and none of them is the single definitive answer. The galaxy is all of these things at once and more. What emerges from this analysis is a picture of a galaxy that is far more extended, more complex, and more dynamic than the bright spiral image that most people associate with the name Andromeda. The bright disk, while visually striking and astrophysically important, is only the innermost, densest part of a much larger structure that extends millions of light-years into the surrounding space. The galaxy is not a static, isolated object, but a continuously evolving system, shaped by its own internal processes of star formation, chemical enrichment, and dynamical evolution, and by its interactions with its environment, including the accretion of gas and the merging of smaller galaxies. Its size is not a fixed number, but a set of numbers, each corresponding to a different physical component and a different observational technique, and all of these numbers have changed over the history of astronomy and will continue to change as instruments and methods improve. The story of Andromeda's size is, in the end, a story about how we observe and understand the universe, about the tools we build, the assumptions we make, and the gradually expanding scope of what we can detect and measure. The progression from Al-Sufi's small cloud to the modern picture of a multi-million light-year scale structure is a remarkable intellectual journey, spanning over 1,000 years and encompassing some of the most profound transformations in human understanding of the cosmos. At each stage, the prevailing view of Andromeda reflected the state of observational technology and theoretical understanding of the time. Al-Sufi saw a nebulous patch because his eye was the only detector available. Messier catalogued it as a non-comet because his scientific purpose was to find comets. Hubble recognized it as a separate galaxy because the 100-inch telescope and Leavitt's period luminosity relation gave him the tools to measure its distance. Baird revised the distance because his understanding of stellar populations revealed a systematic error in the earlier calibration. Modern surveys continue to extend the known boundaries of the galaxy because their instruments are sensitive to ever fainter levels of light. At no point has the galaxy itself changed. What has changed is our ability to perceive and measure it, and each improvement in that ability has revealed a larger, more complex and more interesting object. The question of how big Andromeda really is thus does not have a single answer, but the range of answers, spanning from 100,000 to a few million light-years depending on the definition and the measurement, conveys something important about the nature of galaxies and the nature of scientific knowledge. Galaxies are not simple objects with well-defined boundaries. They are extended, multi-component systems whose properties vary continuously with position, and whose limits are set by the sensitivity of our instruments and the conventions of our definitions. Understanding this, and appreciating the range of physical phenomena that contribute to the size of a galaxy, is a more accurate and more interesting response to the question than any single number could provide. And as our instruments continue to improve, and our theoretical models continue to develop, the answer will continue to evolve, revealing new aspects of a galaxy that has fascinated observers for over 1,000 years, and will undoubtedly continue to do so for as long as human curiosity persists. The deep surveys that have been conducted in recent years, and the ones planned for the near future, are not merely adding decimal places to existing measurements. They are revealing qualitatively new types of structure and behavior that change our understanding of what a galaxy is. The discovery of coherent stellar streams in Andromeda's halo, for example, was not just a refinement of the halo's extent, but a demonstration that the halo is an archive of the galaxy's accretion history, preserving the remains of galaxies that were consumed billions of years ago. The detection of the vast gaseous halo through quasar absorption spectroscopy was not just an extension of the known gas distribution, but evidence for a massive reservoir of baryonic matter in a phase, hot and diffuse, that had not been directly detected before around any galaxy. These discoveries have implications not just for Andromeda, but for our understanding of all galaxies, because they reveal processes and components that are likely universal, but that can only be studied in detail in the nearer systems. The intellectual framework within which Andromeda is understood has also evolved in parallel with the observations. In the early 20th century, the dominant paradigm was one of isolated island universes, separate systems moving through an otherwise empty space. This picture was replaced by the recognition that galaxies exist within a cosmic web of dark matter and gas, interacting with each other and with their environment in complex ways. The concept of a galaxy as a gravitationally bound system embedded in a dark matter halo, surrounded by a circumgalactic medium and connected to other systems by filaments of the cosmic web, is a much richer and more physically accurate picture than the older notion of an isolated island. In this picture, the size of a galaxy is not just a geometric property, but a reflection of its cosmological context, its mass, its formation history, and the properties of the universe as a whole. The study of Andromeda also illustrates the role of serendipity and the unexpected in scientific discovery. Many of the most important findings about Andromeda were not anticipated by the researchers who made them. Hubble was not specifically looking for Cepheid variables when he began his program of photographing M31. He was initially searching for novae. Baird did not set out to discover stellar populations. He was trying to resolve individual stars in Andromeda's bulge. The detection of the giant stellar stream was a byproduct of a survey designed primarily to study the galaxy's outer disk, and the discovery of the extended gaseous halo through quasar absorption lines was enabled by the chance alignment of suitable background quasars behind different parts of Andromeda's halo. These discoveries were made possible by a combination of improved technology, careful observation, and the willingness of researchers to follow up unexpected results rather than dismissing them as anomalies. The interplay between technology, observation, theory, and serendipity that characterizes the study of Andromeda is a microcosm of the broader scientific enterprise. The question of how big Andromeda is may seem simple and straightforward, but pursuing the answer has led to some of the most important discoveries in modern astronomy, including the existence of galaxies beyond the Milky Way, the expansion of the universe, the presence of dark matter, the process of galaxy formation through hierarchical merging, and the existence of vast reservoirs of gas in the circumgalactic medium. Each of these discoveries has, in turn, raised new questions and opened new avenues of research, so that the study of Andromeda continues to be a vibrant and productive field more than a century after Hubble's pioneering observations. In closing this account, it should be emphasized that the numbers cited throughout, the distances, sizes, masses, and luminosities, are not final or absolute. They are the best estimates available at the present time, based on the data and models currently in hand, and they are subject to revision as new observations are made and new analyses are performed. The history of Andromeda's distance estimate, from Hubble's initial value of 900,000 light-years to the current value of 2.5 million light-years, is a reminder of how much these numbers can change as methods improve. The history of the galaxy's perceived size, from a small cloud to a multi-million light-year structure, is an even more dramatic illustration of the same principle. The true size of Andromeda, in the deepest sense, is still being discovered, and each generation of astronomers, with their new instruments and new ideas, will add to our understanding of this extraordinary object, the nearest large galaxy and one of the most studied objects in the history of astronomy.